Look around you for a moment. The room feels solid, stable, predictable. Objects sit where you expect them to sit. Your phone rests on the table. The chair stands on the floor. The floor holds you up. Nothing surprising about any of this. But now notice something we almost never question. Everything around you is being pulled downward. The cup stays on the table because gravity presses it there. Your body rests in the chair because gravity pulls you into it. Even the air in this room has weight. We grow up with this idea so early that it stops feeling mysterious. Of course, things fall. Of course, objects have weight. Gravity pulls everything toward the earth. Simple. But if you pause for a second and really think about it, something strange begins to appear. What exactly is doing the pulling? It's easy to say the word gravity, but the word itself doesn't explain very much. It's just a label. Imagine you drop a pen from your hand. It falls. Everyone knows that. Everyone expects it. But why does it fall? Is something reaching down from the earth, grabbing the pen and pulling it closer? That sounds a little strange when you say it out loud, because there's nothing visible connecting the earth and the pen. No rope, no wire, no invisible hand, just empty space. And yet the pen accelerates downward as if something is guiding it. Now here's where the story becomes interesting. For most of human history, people didn't know how to explain this at all. Objects fell because that was simply their nature. Heavy things moved downward. Light things moved upward. That was the explanation. Not very satisfying, but it worked well enough for everyday life. Then in the 1700s, a remarkable mind began thinking about the problem in a completely new way. The physicist Isaac Newton. Newton looked at falling objects, and he asked the question that sounds obvious today, but at the time was revolutionary. What if the same force that pulls an apple to the ground also holds the moon in its orbit around the earth? That idea changed physics forever, because suddenly the universe looked unified. The falling apple, the orbiting moon, the motion of planets, all explained by a single invisible force, gravity. Newton's equations described this force with extraordinary precision. They could predict the motion of planets. They could calculate the paths of comets. They could even tell you how tides move across the oceans. For centuries, this theory worked almost perfectly. And because it worked so well, people began to imagine the universe in a particular way. Space was thought of as a kind of stage, a vast, invisible arena where the events of the universe unfold. Planets move through it. Stars drift through it. Light travels across it. But space itself does nothing. It just sits there, silent, empty, unchanging. And within this empty stage, forces act between objects. Gravity pulls. Objects accelerate. Everything seemed clear until physicists started asking a deeper question. A question that Newton himself never fully answered. If gravity is a force, how does the Earth actually reach out through empty space and pull the moon? Think about that carefully. The moon is nearly 400,000 kilometers away, and yet somehow the Earth influences its motion. Across nothing, no medium, no contact, just space. Newton himself found this deeply puzzling. In fact, he once wrote that the idea of objects affecting each other across empty space without anything in between was something he found almost impossible to believe. And yet, the equations worked. So for more than 200 years, physicists accepted the mystery. Gravity pulls across space. That was the rule. But hidden inside that explanation was a quiet assumption. An assumption so obvious, almost no one questioned it. The assumption was this: space itself is flat, rigid, and completely passive. It's just the empty background where gravity happens. But in the early 20th century, a young physicist began to suspect something extraordinary. What if that assumption was wrong? What if space is not just an empty stage, but something that can actually bend? And if space can bend, then gravity might not be a force at all. It might be something far stranger. Let's go back to something simple. Imagine you're standing under a tree. A small apple loosens from a branch. For a brief moment, it hangs there. Then it falls straight toward the ground. This moment is so ordinary that most people never think twice about it. But in the 17th century, someone did. The English physicist Isaac Newton. The story of the apple is famous, perhaps a little romanticized. But the real insight Newton had was astonishingly bold. He looked at the falling apple, and he wondered something extraordinary. What if the force pulling the apple downward is the same force that holds the moon in orbit around the Earth? At first, that idea sounds ridiculous. An apple falls a few meters. The moon circles the Earth from nearly 400,000 kilometers away. These two events seem completely unrelated, and yet Newton suspected they were connected by the same rule. To test this idea, he imagined a strange thought experiment. Picture a cannon sitting on top of a very tall mountain. You fire a cannonball horizontally. At first, the cannonball travels forward, but gravity pulls it downward, so the path curves until it hits the ground. Now imagine firing the cannonball faster. It travels farther before hitting the Earth, faster still, and it travels even farther. Eventually, something remarkable happens. If the cannonball moves fast enough, the Earth curves away beneath it at the same rate it falls. Instead of crashing into the ground, the cannonball keeps falling around the Earth. It never lands. It becomes an orbit. That orbit is exactly what the moon is doing. The moon is not floating motionless in space. It is constantly falling toward the Earth. But because it is also moving sideways through space, it keeps missing the Earth, falling forever. This was Newton's breathtaking realization. The same force that pulls the apple to the ground reaches all the way to the moon. And not just the moon. The same law governs the motion of every planet, every comet, every satellite in the solar system. Newton captured this idea in a simple rule called the law of universal gravitation. Every object in the universe attracts every other object. The larger the masses, the stronger the attraction. The farther apart they are, the weaker the pull. That was it. One elegant principle, explaining the motion of the heavens and the fall of an apple. The power of this idea was extraordinary. Using Newton's equations, scientists could predict where planets would be centuries in the future. They could track comets returning after decades of travel. They could even discover new planets just by noticing tiny gravitational disturbances. In fact, the planet Neptune was discovered this way. Astronomers noticed that Uranus wasn't moving exactly as Newton's equations predicted. Something unseen was tugging on it. By calculating the gravitational effect of an unknown planet, they predicted where it must be. Telescopes pointed to that location, and there it was. An entire planet discovered with mathematics. This kind of success made Newton's theory feel almost magical. Gravity became the invisible architect of the cosmos. Planets orbit stars. Moons orbit planets. Galaxies hold together. All because masses pull on one another across space. And yet, hidden inside this powerful theory was a quiet mystery. Think again about the Earth and the moon. They are separated by an enormous distance. Between them, there is mostly empty space. So, how exactly does the Earth pull the moon? Does the Earth send out some invisible signal? Does gravity travel through space like a wave? Or does the moon somehow feel the Earth's presence instantly? Newton's equations could calculate the force perfectly, but they never explained how the force actually works. It simply acted across empty space. Instantly. Even Newton himself admitted that this troubled him, because in the physical world we understand forces usually require contact. You push a door, you pull a rope. Wind pushes a sail, but gravity seemed different. Two objects could influence each other without touching, across vast distances, across empty space. For more than 200 years, physicists lived with this strange idea. The equations worked beautifully, so the deeper question was quietly set aside until the early 20th century, when a young patent clerk began thinking about gravity in a completely new way. His name was Albert Einstein. And what he realized would completely change our understanding of space itself. For more than 200 years, Newton's theory of gravity stood unchallenged. It worked so well that many physicists believed the story was finished. Planets moved exactly as predicted. Comets returned on schedule. The moon followed its orbit with astonishing precision. Gravity seemed completely understood, and yet, somewhere beneath the surface, there was a small crack in the picture. To see it, you have to think about something Newton himself worried about. How does gravity actually travel through space? Imagine the Earth suddenly disappeared, just vanished. What would happen to the moon? Would it continue orbiting for a while before drifting away? Or would it instantly fly off into space? According to Newton's equations, the answer was immediate. The moon would feel the change instantly, because in Newton's theory, gravity acts across space without delay. The Earth pulls the moon, and the moon responds immediately. No travel time, no signal moving through space, just instantaneous influence. At first glance, this might not seem very strange, but think about it more carefully. The moon is nearly 400,000 kilometers away. That's far enough for light to take more than a second to travel. And light, as far as we know, moves incredibly fast, faster than anything else in the universe. So how could gravity act even faster than light? That question sat quietly in the background of physics for centuries. Most scientists simply accepted it. The equations worked. The predictions were correct. Why worry? But in the late 19th century, something began to change. Physicists started studying light more carefully than ever before. Experiments revealed something remarkable. The speed of light appeared to be constant. No matter how fast you moved or where you measured it, light always traveled at the same speed. This result was deeply puzzling because according to classical physics, speeds should add together. If you run forward and throw a ball, the ball moves faster relative to the ground. But light didn't behave that way. Its speed never changed. In 1905, a young physicist named Albert Einstein proposed a radical explanation. He suggested that the laws of physics are the same for all observers, and that the speed of light is a fundamental limit of the universe. Nothing, no object, no signal, no influence can travel faster than light. This idea became the foundation of special relativity. And suddenly, Newton's theory of gravity had a serious problem. Because Newton's gravity required instant action across space. If the sun moved slightly, the Earth would supposedly feel that change immediately. But special relativity said that nothing could travel faster than light. So gravity couldn't be instantaneous after all. Something about the old picture had to be wrong. For Einstein, this puzzle became irresistible. He spent years thinking about gravity, not with complicated experiments, but with simple thought experiments. He imagined elevators, falling objects, observers drifting in space. One day, he had what he later called the happiest thought of his life. Imagine you are inside an elevator. Suddenly, the cable snaps. The elevator begins to fall freely toward the earth. Inside the cabin, something strange happens. If you drop a ball, it doesn't fall to the floor. Instead, it floats beside you. For a brief moment, gravity seems to disappear. You feel weightless, exactly like astronauts orbiting the Earth. This realization shocked Einstein because it suggested something profound. Gravity might not be a normal force at all. Instead, gravity and motion might be deeply connected. The difference between falling and floating in empty space might simply be a matter of perspective. And if that was true, then the entire Newtonian picture of gravity might need to be rewritten. Not just adjusted, not slightly corrected, completely reimagined. Because the real story of gravity might not be about forces pulling objects through space. It might be about something far stranger. The possibility that space itself is not rigid at all. That the stage of the universe can bend. Einstein's idea began with something incredibly simple. Not a giant telescope. Not a massive laboratory. Just a thought experiment. Imagine you're standing inside a small elevator. The walls are smooth. No windows. No way to see outside. You have no idea where the elevator is. It might be resting on Earth or floating somewhere far out in space. Now imagine you drop a ball from your hand. It falls straight to the floor. From your perspective, the explanation is obvious. Gravity must be pulling it down. But Einstein asked a strange question. What if the elevator isn't on Earth at all? What if it's drifting through deep space, far away from any stars or planets? No gravity anywhere nearby. Now imagine that a rocket engine begins pushing the elevator upward, not violently, just steadily accelerating. Inside the elevator, you would feel pressed to the floor. And if you drop the ball again, it falls. Exactly the same way it did before. From your perspective inside the elevator, nothing looks different. The ball falls to the floor. Your feet feel heavy. Everything behaves exactly like gravity. And yet, there is no gravity at all, just acceleration. This realization was extraordinary because it meant something profound. Inside a small enclosed space, there is no experiment you can perform that can tell you whether you are feeling gravity or simply accelerating upward. The two situations are completely indistinguishable. This idea became known as the equivalence principle. Gravity and acceleration are fundamentally the same thing. At first, this might seem like a clever trick, but Einstein realized it had astonishing consequences. Because if gravity and acceleration are equivalent, then gravity must affect everything that acceleration affects, even light. Now that's a strange thought. Light has no mass. So in Newton's theory, gravity shouldn't really influence it, but acceleration certainly can. Imagine again you are inside that accelerating elevator in deep space. A beam of light enters through a small hole in one wall. It travels across the cabin toward the opposite wall. But while the light is moving, the elevator continues accelerating upward. So by the time the light reaches the other side, the floor has moved slightly upward. From inside the elevator, the beam of light appears to bend downward, not because light itself curved, but because the elevator moved. But remember the equivalence principle. Inside the elevator, you cannot tell the difference between acceleration and gravity. So if acceleration bends the path of light, gravity must bend light too. That was the astonishing implication. Gravity does not just affect falling apples or orbiting planets. It affects light itself. This was a shocking prediction because light was supposed to travel in perfectly straight lines. Yet Einstein's reasoning suggested something completely different. Light passing near a massive object, like the sun, should curve. Starlight traveling across the universe should bend as it passes near massive bodies. At the time, this idea sounded almost unbelievable. But Einstein kept pushing the idea further, because if gravity can bend light, then perhaps gravity is not really a force at all. Maybe something deeper is happening. Maybe objects are not being pulled through space. Maybe instead, the space they move through is changing shape. And if space itself can change shape, then the universe is very different from what Newton imagined. Because space would no longer be a rigid stage. It would be something dynamic, something flexible, something that can bend. For centuries, physicists imagined space as something perfectly rigid, an invisible stage, flat, unchanging, silent. Planets moved across it. Stars drifted through it. Light traveled across enormous distances. But space itself did nothing. It was just the background of the universe. Einstein began to suspect that this picture was wrong. Not slightly wrong, fundamentally wrong. The clue came from the strange connection between gravity and acceleration. If gravity behaves exactly like acceleration, then maybe gravity isn't a force pulling objects at all. Maybe something else is happening. To see the idea, imagine a very different kind of world. Picture a tiny creature living on the surface of a huge sphere, a planet perhaps. But suppose this creature is extremely small, so small that the surface of the sphere looks perfectly flat. As it walks around, everything appears ordinary. Straight lines look straight. Distances behave normally. The creature believes it lives on a flat world, but in reality, the surface is curved. The creature simply cannot see the curvature directly. Instead, the curvature reveals itself through motion. Imagine the creature begins walking in what it believes is a perfectly straight line. Eventually, it returns to where it started. No turns, no corrections, just a straight path around a curved surface. To the creature, this would be deeply mysterious. Something must be bending the path, but in reality, nothing is pulling it sideways at all. The surface itself is curved. Einstein realized something astonishing. Maybe the same thing is happening in our universe. Perhaps objects moving under gravity are not being pulled by a force. Perhaps they are simply following the natural paths in a curved geometry. In other words, space itself might be curved. And if space is curved, then planets orbit stars not because they are pulled, but because they are moving along the straightest possible paths through curved space. This idea sounds strange at first, but consider something familiar. Airplanes traveling long distances across Earth rarely fly in straight lines on a map. Instead, they follow curved routes across the globe. These paths are called great circles. To a passenger on the plane, the flight feels perfectly straight. But from space, the path curves around the Earth. Because the surface itself is curved, Einstein proposed something even more radical. Not just curved surfaces, curved space itself. And even more surprising, space was not separate from time. The two were woven together into a single fabric called space-time. In Einstein's new picture, massive objects like planets and stars do something remarkable. They distort the geometry of space-time around them, not by pulling on objects directly, but by reshaping the structure of the space those objects move through. A planet orbiting a star is simply following the straightest path through that curved space-time. From far away, that path looks like a curved orbit. But locally, the planet is simply moving straight ahead, just like the creature walking across a curved world. In this new view, gravity disappears as a force. Instead, gravity becomes geometry. Matter tells space-time how to curve. And curved space-time tells matter how to move. That simple sentence captures one of the deepest insights in physics. But to really understand it, we need to learn how to visualize something incredibly strange. A universe where the straightest possible path can look curved. Now we arrive at a subtle idea. One that sounds simple at first, but changes the way you think about motion entirely. What does it mean to move in a straight line? It feels like an obvious question. If you throw a ball in empty space, with nothing pushing or pulling on it, it travels straight. That's the rule we learn in school. But Einstein realized something surprising. The idea of straight depends on the geometry of the space you're moving through. To see why, let's go back to the surface of the Earth. Imagine you are standing at the equator. You begin walking north. You keep walking, always heading straight ahead. No turns, no sideways motion. Eventually you arrive at the North Pole. Now imagine turning 90 degrees and walking south again. Eventually you return to the equator. If you draw this journey on a globe, you form a triangle. But something strange happens. The angles of that triangle add up to more than 180 degrees. That would be impossible on a flat surface. But on a curved surface, geometry behaves differently. Straight paths begin to bend relative to each other. Physicists call these natural straight paths geodesics. A geodesic is simply the straightest possible path in a given geometry. On a flat plane, a geodesic is an ordinary straight line. On the surface of a sphere, a geodesic becomes a great circle. Airplanes follow them. Satellites trace them. Not because something pulls them sideways, but because the geometry itself guides the path. Einstein realized that the same principle could apply to the universe itself. Objects moving through space-time naturally follow geodesics, the straightest possible paths through the geometry of space-time. But when space-time is curved, those paths appear curved to us. Think about the Earth orbiting the Sun. In Newton's picture, the Sun pulls the Earth inward with a gravitational force. But in Einstein's picture, the Earth is simply moving along a geodesic. The Sun's mass curves space-time around it, and the Earth follows the natural path through that curved geometry. No invisible rope, no pulling force, just motion through curved space-time. To visualize this, people often use a famous analogy. Imagine stretching a large rubber sheet. Now place a heavy bowling ball in the center. The sheet sinks inward, creating a curved depression. If you roll a smaller marble across the sheet, its path curves around the bowling ball, not because the bowling ball is pulling it directly, but because the surface it moves on is curved. This analogy isn't perfect. The real universe has 4 dimensions, 3 of space and 1 of time, but it captures the essential idea. Mass bends the geometry of space-time, and objects move according to that geometry. Even light follows these paths. When a beam of light passes near a massive star, its path curves slightly. The light is not being pulled like a tiny particle. Instead, the space-time it travels through is curved, so the straightest possible path becomes a curved line. This realization completely changed the meaning of gravity. Gravity was no longer a mysterious force acting across empty space. Instead, gravity became the shape of space-time itself. Planets orbit stars because space-time curves. Light bends because space-time curves. Even the flow of time changes in strong gravity. And once physicists began to understand this, they realized something even more astonishing. The universe itself might be shaped by this geometry. Galaxies, black holes, even the expansion of the cosmos. All of it governed by the curvature of space-time. But a theory this radical needed proof. And that proof would arrive in one of the most dramatic experiments in the history of science. Einstein finished his new theory of gravity in 1915. It was called general relativity. At its heart was a breathtaking claim. Gravity is not a force. Instead, mass bends space-time, and objects simply move along the natural paths within that curved geometry. It was a beautiful idea, elegant, deep, mathematically powerful. But beauty alone does not make a theory true. Science demands evidence, and Einstein knew exactly where to look for it. Remember the strange prediction we discussed earlier. If space-time curves near massive objects, then light passing close to a star should bend slightly. That meant starlight passing near the sun should shift direction. But there was a problem. Stars near the sun are normally invisible during the day. The sun's brightness washes them out completely, except during a solar eclipse. When the moon passes directly in front of the sun, the sky suddenly darkens. For a few minutes, stars become visible near the sun's edge. If Einstein was correct, those stars should appear slightly displaced. Their light would curve as it passed through the sun's distorted space-time. In 1919, an expedition set out to test this idea, led by the British astronomer Arthur Eddington. Teams traveled to remote locations where a total solar eclipse would be visible. One group went to an island off the west coast of Africa. Another traveled to Brazil. Their mission was simple in principle, but extremely difficult in practice. Photograph the stars near the eclipsed Sunday. Then compare their positions to photographs taken when the sun was elsewhere in the sky. If Einstein was right, the stars should appear shifted outward slightly because their light had curved around the Sunday. When the measurements were finally analyzed, the results were astonishing. The starlight had bent exactly by the amount Einstein predicted. Almost overnight, Einstein became world famous. Newspapers around the globe announced a revolutionary discovery. The geometry of space itself had been confirmed, but that was only the beginning. Over the decades that followed, experiment after experiment confirmed the theory. Astronomers discovered that the planet Mercury's orbit slowly shifts over time. Newton's gravity couldn't fully explain it, but Einstein's curved space-time predicted the shift perfectly. Then came an even stranger phenomenon, gravitational lensing. Massive galaxies can bend the light from objects far behind them. The result is extraordinary. Distant galaxies appear stretched into arcs, or duplicated into multiple images. Sometimes a perfect ring of light appears around a galaxy. These are called Einstein rings. They are among the most beautiful structures ever observed in the universe. And they exist for one reason, because space-time bends. Then came an even more dramatic prediction. If space-time can bend, it might also bend so severely that nothing can escape. Not even light. These objects became known as black holes, regions where space-time curves inward so intensely that all paths lead deeper inside. For decades, black holes were only mathematical predictions, But today, we observe them throughout the universe. In 2015, another prediction of Einstein's theory was confirmed. Scientists detected gravitational waves, ripples in space-time itself, produced when massive objects like black holes collide. These waves traveled across the universe for billions of years until they finally passed through Earth, stretching and compressing space-time by tiny amounts. Sensitive instruments detected those ripples. For the first time in history, humanity had measured the vibrations of space-time itself. All of this confirmed a once unthinkable idea. Space is not empty. Space is not rigid. Space can bend. And once you accept that, the universe begins to look very different. Because if space-time can bend, then the fabric of reality itself may be far more dynamic, far more alive than we ever imagined. Once you accept Einstein's idea that space can bend, the universe begins to look very different. Because the stage of reality is no longer passive. It's not just a background where events happen. Space itself becomes part of the story. Imagine the universe again, but this time not as an empty container. Instead, picture it as a vast, flexible fabric. Every star, every planet, every galaxy presses into that fabric. Mass shapes space-time, and in return, space-time shapes motion. That relationship runs the entire cosmos. Galaxies orbit each other because space-time curves. Stars cluster because space-time curves. Even the paths of light across billions of light years are guided by the shape of space-time itself. But once physicists began thinking this way, they realized something even more astonishing. If space-time can bend, then it might also stretch, or ripple, or even expand. And in fact, that is exactly what the universe is doing. In the 1920s, astronomers studying distant galaxies noticed something strange. Almost every galaxy in the sky appears to be moving away from us. Not because they are flying through space like shrapnel from an explosion, but because the space between galaxies is expanding. The fabric of the universe itself is stretching. Galaxies ride along with that expansion, like dots drawn on the surface of a balloon as it inflates. The dots move apart, not because they are crawling across the rubber, but because the rubber itself is expanding. This discovery transformed cosmology. It suggested that the universe had a beginning, a moment when space-time itself emerged, hot, dense, and rapidly expanding, what we now call the Big Bang. But the story doesn't stop there. If space-time can stretch and bend, then perhaps it can do even stranger things. Near a black hole, space-time curves so intensely that time itself slows down. A clock near the edge of a black hole ticks more slowly than a clock far away. This isn't science fiction. It's something we measure every day. Even the satellites used for GPS navigation must correct for this effect. Because time passes slightly differently in orbit than it does on Earth, all because space-time is curved. And if space-time can ripple, then the universe is not silent at all. It vibrates. Massive collisions between black holes send waves through space-time itself. Ripples that cross galaxies, clusters of galaxies, entire cosmic voids, until eventually those ripples pass through Earth, through you, through everything. And you never notice, because the distortions are unimaginably small, yet they are real, which brings us back to the question that started all of this. Why can space bend? The honest answer is that physics doesn't yet know why at the deepest level. Einstein's equations describe how space-time bends. They predict its behavior with extraordinary precision, but the ultimate reason why the universe is built this way remains one of the great mysteries of nature, and perhaps that is the most beautiful part of science. Every answer opens another question. Every discovery reveals a deeper layer of reality. We began with something ordinary, a falling apple. But by following that simple observation far enough, we arrived at a breathtaking conclusion. The universe is not a rigid stage. It is a living geometry, a fabric that bends, stretches, and ripples. And everything that exists, every planet, every star, every galaxy, moves through that geometry, following paths written into the shape of space-time itself. which means the next time you drop something and watch it fall toward the ground, you're not just seeing gravity, you're watching the curvature of the universe in action.